Hello, everybody. Hello from Germany, in Ludwigshafen. I am from BSF, and I hope you are having a nice day today. I will try to say some words regarding notching of polymers for fracture mechanics. It's supposed to be a little bit more practical, and I think it's not a bad idea to have this more practical session at the end of the day after such a long day. So I guess now we are all familiar with the purpose of fracture mechanics, I don't want to get too much into details here, and just put some slides just to highlight what we intend to do here. But as you know, we are dealing here with understanding the mechanical behavior of our polymers that have uh, cracks. We know that due to the presence of this crack, we have at the crack tip some stress concentration that leads to a earlier failure of the structure. And of course, we need to be able to describe that, to understand that. And this is why we need some appropriate testing method for that. And we have been developing in the past some standards that have been accepted by ISO. Today, I'm discussing about notching for materials that are respecting the linear elastic behavior, or that have a linear elastic behavior, but this kind of approach is also applicable for materials that are non-linear elastic, for example. Yeah? And regarding when we are describing the crack resistance of our polymer materials, as you have already learned today, we are considering we use the energy release rate, that is at the end the energy release rate that is released from the growth of the crack. And we also use the stress intensity factor that has already been fully described this morning. And here you can see once again the expression, and it shows us how it is related to the stress that is applied to the material during the testing, and also to the crack geometry, and to the crack autogeometry of the sample. So as you already heard today, we have stress concentration. The stress is increasing as we are coming close to the crack tip, and we have some singularity at the crack front that leads to some. So what we observe indeed at the crack front is a more plastic zone, and this is here shown how the plastic zone looks like. And when we are using the linear elastic fracture mechanics, we need here to respect the plane strain state, and for that we need to have some samples that have a certain thickness to be able to have in the mid section, in the middle of the thickness of the sample, to have this plane strain state. Why we need that is to ensure that we have just a localized plastic zone. So all this information you got already this morning. This is why I really went through it quite quickly. Now I would like to go more into the real content of my presentation today. It's to discuss about the notching itself. So as you can imagine, when we want to determine the fracture toughness of our polymers, we need here to have an initial crack. And the standard, the ISO standard that suggests some, or gives some inches regarding this initial crack. At the end, the crack should be as close as possible to a natural crack. So, and what is somehow missing at this stage, it's a real description of how we can achieve this natural crack. Here on the right of my slide, you can see, so when we are testing the fracture toughness. So when we are measuring K1C or J1C, here we are testing under mode 1 condition and under tension loading at the end and the crack tip. So in the standard we have two types of geometries that are suggested. Here this is a single end notch beam test, and we did at the beginning. So let's say that I forgot to mention that we are, what I'm presenting now, it's a kind of review of the activities that we have been doing within TC4 within the last years, and we recently, or it was 2-3 years ago, we started a round robin on this topic, on notching, on the impact of notching on the properties we were measuring, and we started using the same mud. We tested an epoxy system, and we didn't provide any significant recommendation regarding how the notch should be brought or generated in the sample. And as you can see, we ended up with quite large scattering within the different labs that were involved in this testing campaign. So based on that, we initiated this activity on targeting to propose in the future a repeatable and reproducible approach for notching of the samples. So in this slide, you can see an overview of the different approaches that are generally used in order to induce this initial crack. So you have the so-called fatty crack growth approach, which consists at the end to use a fatigue machine to load it dynamically the sample and to propagate with this approach the crack in some millimeters in order to have a natural crack. This is a really good approach regarding the quality of the notes that you are generating. The drawback of this approach is very time consuming, and not all labs, I must say, particularly in industrial environment, have the requirement, the equipments in order to generate this kind of crack. So we need here to have, we are considering a standard, and we need to have an approach that can be applied by most of the people without too much of equipment, and also with not as high expertise as the technicians that we have, or the people having in most of the labs in academia. Another approach, which is, I must say, the most typically used, is the tapping approach, and it consists of using a simple razor blade and to tap the razor blade and generate at the end a crack that will propagate further. Another approach is using the pushing. In that case, the blade is pushed through the already pre-notch with. I didn't mention that, but typically in the first step we need to pre-notch or to prepare the notch at the first stage with a milling machine. I will show you that more in detail in the next slides. These two last methods I mentioned are quite similar, but they are also, I must say, at this stage, very dependent on the skill of the technical person that is doing that. And when you work, especially with tapping with brittle materials like epoxy, this is very common that the load that you apply at the taping is too high, and that the crack propagates so fast that the material will be totally, or the sample will break, what you don't want. So you are really, in this case, the risk to lose a lot of samples. One approach that we are thinking that is much more appropriate for this kind of approach, or of target, let's say that way, is the cutting. So cut is a cold cutting method. In that case, here we are bringing a razor blade also when we are cutting, like when you using a knife, the sample, and I will explain you how we do that, and we need, of course, to have specific steps to be sure that we have a reliable and repeatable crack at the beginning of the test. So here is a kind of overview of the different steps that must be followed during this entire sample preparation. You start from the coupon, the sample that you have, and as I mentioned, you come before with a specific. You can come here with a milling machine to initiate the first V notch, and that is at the end this initial V notch here. And what we are speaking about is here this remaining additional crack length that you need to have. So in the first V notch, you will generate that with this milling machine, and after we come with the blade and bring this additional smooth crack. And for that, we need to be cautious and to use to be sure that the blade that we are using is good enough. So I must say that along the different when you have too much of sample preparation, or when you are preparing in a row many samples, it's not rare that you have some wearing of the blade, and you need to be sure that it is not damaged, otherwise it will have an impact in the accuracy of the initial cracks that you are generating. So now some small details regarding how we bring the crack with the razor blade in this additional phase. So typically what we do, we stack 3 samples, and we use additionally also a sacrificial specimen that has a specific purpose, is that when you come with the blade and after when you see how in this small animation the kind of movement that we are inducing with the blade in order to ensure that that the quality of the note will be the same, of the crack will be the same in both sides of the sample, and this sacrificial sample is contributing to ensure that. So as you can see, we also cut the blade before, and we also apply a specific angle in order to be sure that we are cutting with the quality that we required. So we have been doing in the past many parametric studies involving or studying the impact of the different angles here, the different aspects of the blade, and we learn. So we worked on different materials, and we learned that having this clearance angles and rake angles in this range, we achieve the most reproducible and repeatable quality of the crack. So here are some recommendations that that we propose in order to achieve this smooth crack before testing. What I didn't mention is that we do it progressively. So we are not doing just in one step. So I'm redoing the video. We do various steps. Actually, we do at least 4 or 5 steps, and we are also varying the speed during the process. And as we are getting close to the end of the wished target crack length, we are making finer steps, so we can control how much we are going into the material by each step. And one important aspect that we are also doing is looking at the quality of our nodes afterwards, because as we will see in the rest of the presentation, this will have a significant impact in the quality of the results. So here is an overview of different equipment that have been used in the different labs that are involved in this activity. And you can see that we at BSF, we are using quite a complex system, but with very simple equipments like this microtome equipment, you can already achieve a quite nice quality of notch or of crack. So here is to summarize again the how the sample looks like and how the crack looks like. I won't speak so much into detail into that because you already saw this information, Joe got this information during this morning, and also due to lack of time, I don't want to go into in details. But during the test, as you mentioned this morning, so we are having an increase of the load, and we must be ensuring that we are fulfilling the linear elastic fracture mechanics, and this is done by testing regarding also when the crack is initiating. So here is how we calculate afterwards the stress intensity factor, and as I mentioned at the beginning of my presentation, we need to be sure that the sample is thick enough to be sure to ensure the plane strain state. Okay, here it's how the curves should look like when you have quite repeatable and reproducible crack. So we tested here 10 samples, and you can see that we have a quite reproducible stress or the stress displacement, or K1s in this case, but load displacement curve, and this is what you don't get, or what you get when you don't have a repeatable, or when I wanted you to show with this slide that the curves we are getting is of course influenced by the original length that we have during the test. So we did different round robin campaign during the last years, and one of the campaign consisted of that we here at BSF we prepared the samples and sent all the samples to the different labs that were involved in the round robin campaign, and as you can see, we got quite similar results in the different labs. This was showing to us that the repeatability of the approach that we are using is quite high, which is quite promising. We sent another sample set to the different labs, and without giving so much recommendation how the samples should be prepared. And you see here that the scattering that we got was significantly higher. And why is that? And so here, if you look at the microscopy of the samples after being notched, you can see that they have different aspects, or different, indeed they look like different. So and here, for example, you can see that in some cases, so this set was tested in one of the labs, and you can see that in the case of some samples, so we can see at this crack tip some blunting that may occur due to the notching process itself. What we observed is that the samples that delivered the lower K1C value were the one that had the really sharpest notch. And as in the contrary, you can see that when we get a very large notch, we have simultaneously also larger K1C values. Okay, and in the last set, what we did, we sent then additional recommendations to the different participants of round robin, and as you can see here, the scattering is at this stage significantly lower. We were quite surprised, especially by these high values, and we wanted to have better understanding of why those values are so high. And here, as comparison, you can see the values that we got. As reference, we used this other approaches. Basically, so we used the fatigue crack growth method to induce a pre-crack, and you see that it delivers lowest values than the one that we are getting with this cutting approach. And we did tapping also, which because it is the most commonly used in when you want to do it quick and dirty, let's say like this. And you see that we are getting very lower values compared 50% lower than the one that we're getting with the other approach. So regarding the high values that I was showing here, so we had a quick overview also on the aspect of the notch, and as you can see here, this is definitely not as smooth as the one that we are getting with the in other labs, and this has also for impact that when you look at the fracture surface at the end, that you have a definitely different fracture surface during the test. This is one of the reasons why we have this much higher value in this lab. I wanted to say some last words regarding the taping itself. As you can see, this is what we got with taping, and we definitely so here this is starting from the pre-notch sample with the milling machine, and as I mentioned, we propagated further with just taping, and as you can see, we have very unclear crack fronts, and we also have different crack planes, and this ends up this is what's happening when you look with microscopy at the end, and you see that we have really very unclear crack front and crack propagation. And contrary, when you look to the fatigue pre-cracked sample, you can see that you have a really smooth and very defined crack front. And here, just to remember what we are getting with the razor blade when we are doing the cutting. Okay, so to conclude, what we observed within the last years is that using this cutting approach, we can definitely produce reproducible and repeatable cracks. And we are somehow overestimating a little bit the K1C value that we are getting with the fatigue crack growth approach. But especially for industrial application, when you need to have an approach that can be repeatable and reproducible, it seems to us that is a very promising approach. I would like to thank all the colleagues that are mostly here on this stage here, and for their contribution along the last years on this project, and thank you very much also for